Everybody, welcome back to another video lesson. Today we're going to go ahead and look at calculations using strong and weak acids. We're going to focus on the calculation of pH, but there are other ways and other things that we can calculate, but I'm going to focus on this because it's pretty much the big picture and what we most commonly calculate when we deal with acids. Okay, so I'm going to start with the easier one, which is the pH of strong acids. Now remember, there are 7 special strong acids. They're going to follow these rules. They shift completely to the right, so there is no Ka. Essentially, there's no equilibrium that we have to deal with. We just have to focus on the fact that this acid completely dissociates into ions. So mathematically, what that means is that if I have a solution that is starting off as a 0.15 molar HCl, so what that means is I'm taking hydrochloric acid and I'm dissolving 0.15 moles in every 1 liter to make the solution. So therefore, what I'm doing is I'm starting with the strong acid. So I'm going to go ahead and write that in here. So this is going to now be a BCA table. Notice that I have a full arrow to the right because there is no equilibrium. The reaction goes completely to the right, so therefore this is going to run out. So initially, I am going to start with, let me click on my pen here. I'm going to start with 0.15 molar HCl. I start off with 0 of the hydrogen ion and 0 of the chloride ion because the reaction hasn't happened. It hasn't dissociated yet because we're at the beginning. As it dissociates, as it starts to do its thing, this is going to go down, this is going to go up, and this is going to go up. So this follows along with the same pattern that we did for stoichiometry back, well, pretty much forever. Anyway, so when the strong acid reacts and it does its thing, this is going to go to 0 because we're not going to have any of that strong acid left over when we're finished. It is all going to go to 0 molar. And over here, we're going to have 0.15 molar for the hydrogen ion, and again, we're going to have 0.15 molar for the chloride because the reaction shifts completely to the right and this will run out. That's the definition of, I guess the definition, but that's how we deal with BCA tables or stoichiometry. So the moral here is that HCl, whatever the strong acid concentration is, okay, that's going to be equal to your hydrogen concentration every single time. So technically you really don't have to do this whole BCA table because whatever this number is here, whatever you end up with for this, right, is always going to go down and form this here. So the hydrogen and the strong acid are going to be the same. So to finish this problem, all I need to do to find my pH is take the negative log of that concentration of hydrogen, which is 0.15, or in this case it could be the strong acid. So pH equals, if you take the negative log and you do that calculation, you're going to end up with 0.82 pH. Notice it's a pretty low pH because, again, this is a strong acid, so it makes sense that we get a large amount of hydrogen ions and that our pH should be relatively low in this respect because it's a strong acid. Okay, again, that's going to be true for all of the other 6 strong acids. So what do we do when we don't have a strong acid? What do we do when we have a weak acid? Now, this is where we're going to introduce something called an ice table. Okay, an ice table starts with initial change, but instead of going to completion, we're going to hit equilibrium. Because remember, in equilibrium, all of the material is present. All of the reactants are there. All the products are there. So we're starting with the HF, the hydrofluoric acid, which is a weak acid, and we're going to end up with hydrogen ions and fluoride ions all in the same container at equilibrium. So we're not going to have anything go to 0. So how do we deal with that? How do we calculate it when we have that situation set up? So I'm going to show you a little trick we can do because we know something about these Kas for the weak acids. So I'm going to start it off the same way. Here's our example. What is the pH of a 0.15 molar hydrofluoric acid? So I'm looking at this question. I'm first noticing that this is a weak acid, right? That's what I first want to notice, is that this is a weak acid, because I notice if it's a weak acid, it's going to really change the way I deal with this problem. Of course, I'm looking for pH, so I'm going to try to find the concentration of the hydrogen ion, but I want to find it at equilibrium. So I'm going to start the problem off just like I did for the strong one. I'm going to put the 0.15 here because that's what I'm starting with, right? I'm putting this into solution. This will start off as 0 molar. And this will start off as 0 molar as well because there's none of those in here. Okay, so what I'm going to do is I'm going to have the reaction now go to equilibrium. Again, this is going to go down by x. This is going to go up by x, just like in our last problem, and just like we do for all the stoichiometry we've done. Again, it's all 1-to-1 ratio, which most of these acid problems are going to be that way. Now, here's the catch. This is not going to go to 0. It's going to go to 0.15 minus x. This will go to x, and this will go to x, because 0 plus x gives us x, 0 plus x gives us x. We can't figure out what x is directly in here like we did in the last problem. If we go back to the last problem, we could easily figure out what the value of x was because we knew that this went to 0, so we therefore knew that this had to go up. Problem here is that we can't do that directly because of the fact that we can't solve for x right away. But there's a way to get around this. To do that, what we're going to do is we're going to focus on the fact that our Ka, we know something about it. So our Ka expression is equal to the concentration of the hydrogen ion, okay, times the fluoride ion over the weak acid. Okay, so that's our expression for the Ka. Now, we can find the value of Ka. We can look it up, or usually in the problems it'll be given to you. I just didn't put it in the problem. I'll go back to my table. My Ka is 7.24 times 10 to the minus 4. So that would be the Ka for this weak acid. So Ka equals, I think I said 7.24 times 10 to the minus 4. Okay, whoops, minus 4. Let's try that again. 4. Okay, so that's my Ka for this particular weak acid. So we know that it's going to favor the reactants, right? There's not going to be very many ions in solution. Notice that the amount of hydrogen ions are very, very low in concentration in relation to the amount of weak acid. So here's the trick. Since Ka is so small, right, such as a small, small number, and the shift to the right is going to be so small, we're going to shift to the right just a little bit, we can say that this change in x is going to be very, very, very small. We can say that it is so small in comparison to the 0.15 that we can say that this amount here can go away. We don't care about that change. So essentially, to us, it's going to look like the hydrofluoric acid doesn't change at all. I know people have a hard time wrapping their brains around this in the beginning, but it's based on the fact that the significant figures are not that, well, they're important, but that's the whole point, is that that number isn't going to change much if you put back the x. So let's go with this. Just bear with me for a second. All right, well, I'll show you the logic in a second here. Okay, so we've got this set up here. All right, what I'm going to do now is I'm going to plug everything in because I know that this is going to stay essentially the same, and then I can calculate x. So let's go ahead and do that. We know that the hydrogen ion is x. Oh, geez, what's going on here? Try that again. Is x, and we know that the concentration of the fluoride ion is also x. We're going to put that all over 0.15, and that's equal to 7.24 times 10 to the minus 4. All right. Now, if I go ahead and I solve for this, I can solve for x because this will be x squared on the top, so it'll be x squared is equal to 0.15 on the bottom. I have a little bit of trouble with my pen today. Sorry about that. Oops, 7.2 times, stop doing that, times 10 to the minus 4. All right, so I'm going to solve for this algebraically. I'm not going to do this step by step, but when I do, my x value, which is equal to my hydrogen concentration, which is also equal to my fluoride, which I'm not really concerned about right now, but it would also be equal to that fluoride, is going to be equal to 0.010 molar. When I actually calculate x and simplify that, x is this number here. Now look at this. Compare this back to 0.15. If I put this back in and I subtract that out, this only goes from 0.15 down to 0.14. Not that big of a deal, but because remember that last digit is always uncertain. This could already been a 4. It could be a 1, could be a 2. Remember, there's an uncertainty in that last digit, so therefore it's not going to really have any impact on the number. So if you want to, plug it back in and solve for the value here and reduce it. That's fine, but it's not really going to make a difference, to be honest. So now what I can do is, now that I have my hydrogen concentration, I can now calculate my pH, which is the negative of that value. So I just take the negative log of 0.010, and I end up with the pH of 1.98. Now take a look at this. pH here is 1.98. If I go back and I compare it to the strong acid was 0.82. Now, they're the same concentration. They both were 0.15. It's just that this one is a weaker acid. It's still pretty acidic. I mean, it's pretty low on the scale, but it's a lot less acidic than the strong one because the ions are not very, there aren't a large amount of ions. So what I'm doing here is I have 0.15 for this one here. That's what this is, 0.15 molar for the weak acid. This really is only going to give us a 0.010 molar. We don't give very many ions in solution. So we start off with this, and it dissociates into a very, very small. When we compare the amount of acid that we started with, not much of it changed at all. And that's the essence of weak acid problems. And this is how you're going to solve them every time, well, almost every time, based on the fact that Ka is really, really small. So there you have it. Thanks again for watching. Talk to you soon.